Hi everybody, welcome to another video in Calculus 3. We go to section 15.4, chain rule. So the chain rule in Calculus 1, let me just write out quickly. So in Cal 1, the chain rule, let's say we have z is a function of u, and then u is a function of x. So we can write z as a function of g of x. Or we can say like that. And with that structure, the derivative of z with respect to x is going to be derivative and then derivative of the parentheses. Right. So that is the chain rule in Cal 1. Now, go to Calculus 3. Calculus of multivariables will be different because we have more than one variable. So there will be a lot of different chain rule, depends on how many variables we have. First, the most simple form is that we have z as a function of x and y, and then x and y a function of t. In that case, derivative of z with respect to t is given like this. So another way to visualize this is we start with the function z. We have two variables x and y. And each one of them is a function of t. And now if we want to find the derivative of z with respect to t, we're going to go this route from z to t, and then we go this route from z to t. So to go from z to all of the t's, we go z to x, from x to t, and from z to y, from y to t. So that's why we have here z to x, then x to t, z to y, and then from y to t, right? Now, the x to t, x is the function of only variable t, so that's why we have the regular derivative, as z have two variables, z has two variables x and y, so that would be partial derivative. So we just use the proper notation. If there's more than one branch, more than one variable, we use partial derivative. If there's only one, we use the derivative. Right, so it's easy enough. Now, example, let z be this function. Of course, it only depends on x and y, and then x is a function of t and y is a function of t. So we have exactly that diagram. So we're going to write dz over dt. That's what the question asks us to find. We go from z to x, partial derivative, and then from x to t is just derivative, and then plus from z to y, and then from y to t. Right, it's important to draw the diagram. Now dz with respect to x, what is that? Derivative of z with respect to x. I'll switch different colors so it's easy to follow. This is the function z. Z with respect to x is going to be derivative of x squared is 2x. Derivative of 3y squared with respect to x, y is a constant. The derivative of constant is 0. Derivative of constant is 0. So we only have 2x where derivative of z with respect to x. Now, and then x equal to cosine of t and y equal to sine t. Derivative of x with respect to t is going to be negative 2 sine t. And then plus derivative of z with respect to y. X squared is a constant. Derivative of constant is 0. Negative 3y squared. Derivative is negative 6y. 20. Derivative with respect to y. Derivative of constant is 0. So that's all we have. And derivative of y with respect to t. Derivative of 2 sine t. 2 cosine t. Right. Oh, so that's simple enough, right? Now, notice we only have t is equal to pi over 4. We don't have x, we don't have y, but we certainly can find it. So next, 2x. X is equal to 2 cosine t, right? So I'm going to put 2 cosine t here. That is for x. For that x. And then I still have negative 2 sine t. And then plus minus 6. Y here is 2 sine t. And dy over dt is 2 cosine t. Right, multiply across 2, 2, and negative 2, that's negative 8 cosine t sine t. And that gives us negative 12, 2 and 2, negative 12 times 2, negative 24. Also cosine and sine. Negative 8, negative 24 is negative 32. Cosine of t sine t. Right. So we take the derivative, just draw the diagram, take the derivative, and we just multiply it. Now, at t equal to pi over 4. So I have negative 32 cosine of pi over 4 sine of pi over 4. Cosine of pi over 4, that's 45 degrees. So we have 2 over 2. And sine is also square root of 2 over 2. That's what we have. And then 2 and 2, square of 2 times square root of 2 is 2. So we have square of 2 and square root of 2, that is 2 times negative 32. Negative 64 over 4 is negative 16. So yes, that's what we have, negative 16. Right. So that is the chain rule, which is simple enough, right? So we start with that, and then just find each one. And even though we have x and y, we can substitute back. X is 2 cosine and y is 2 sine. Substitute into x and y, and then just evaluate at t. That's what we have. Right. So that is one case where we have z is a function of x and y is a function of t. Right. Next, we have different form. Let z be a function of x and y. Z is a function of x and y, where an x and y are function of s and t. then we have derivative of z with respect to s and derivative of z with respect to t as follows. So let's once again we draw a diagram. We start from z. Z has two variables, x and y, and each x and y is a function of two variables s and t. So if we want derivative, we can from with respect from z to s and then from z to t, we can go from z. If we want from z to s, so z to s, this one round, we can also go this round, z to y, then from y to s. So that is derivative of z with respect to s. There are two paths, z to x, x to s, z to x, x to s, and z to y, y to s. So that's what we have. And this is derivative of z with respect to s. Now, if we want derivative of z with respect to t, we go from z to x, then from x to t, and then from z to y, and then from y to t. Just need to close the door. And notice that in this case, z has two variables, so that is partial derivative. And x and y also have two variables, s and t, so all of them are partial derivative. If we just have one, we're going to use the d, which is the regular derivative. Right. So the question answers, what is dz over ds? Don't even need to memorize this. We just go z to x, and then from x to s. Or we can go from z to y, and then from y to s. We'll find two derivatives. Right. So derivative of z with respect to x. With respect to x, we're talking about this function. And this function is a function of x, which is a variable. And cosine of 3y, cosine of 3y is going to be just a constant, because the derivative of that constant is 0. But like I said, we're just going to, the constant will stay. So first, derivative of z with respect to x. Again, let's just color code here. The derivative of z with respect to x, derivative of sine 2x is 2 cosine 2x. And then cosine of 3y is a constant, will stay there. Next, we have x is a function of t and s, y is a function of t and s. Now we have derivative of x with respect to s. Derivative of this with respect to s is just 1. And derivative of this of t with respect to s is 0, because with respect to s, t is a constant, so that's still 0. So that's what we have. We're going to add derivative of z with respect to y. With respect to y, sine of 2x is a constant, so we have sine of 2x. And then cosine of 3y, derivative is negative 3 sine of 3y. And then derivative of y with respect to s, derivative of y with respect to s is just 1. Negative t is constant with respect to s. So we still have 1. So that's what we have. So we're going to have just 2 cosine of 2x, cosine of 3y, and that is minus 3 sine of 2x and sine of 3y. So that's good and all, but this one, the function is to be in terms of s and t, so we substitute back in, and we have 2 cosine of 2. X is s plus t and then cosine of 3, y is s minus t, minus 3 sine of 2, s plus t, and then sine of 3, y is s minus t. Remember, the answer has to be in terms of the bottom variable, s and t here. Right, and I will do the same thing for dz over dt. So dz over dt, once again, it's going to be that. But of course, we can also use the tree diagram. Right. So dz over dt, derivative of z with respect to t, z to x, x to t, and z to y, and y to t. Z to x, x to t, all of them are partial derivative because a function of more than one variable. Z to y, y to t. Right, first, derivative of z with respect to x. Derivative of z with respect to x. So it's going to be 2. 2 cosine 2x. And then cosine 3y is constant, we stay there. Derivative of x with respect to t is going to be 1. Derivative of this with respect to t, s is constant, will be 0. Derivative of t with respect to t is 1. Derivative of z with respect to y is going to be this, sine of 2x. Derivative of cosine of 3y with respect to y, negative 3 sine 3y. And then derivative of y with respect to t, y with respect to t is negative 1. Right? Multiply out. 2 cosine 2x, cosine 3y. And that minus 3 minus 1, so that plus 3 sine of 2x, sine of 3y. And finally, we need to write everything in terms of s and t. So 2 cosine of 2, x is s plus t, y s minus t, 3 sine x s plus t, then sine y minus t. Y is s minus t. That's what we have. So it's not that bad, right, with the tree diagram. But what I'm going to show you a little more advanced. It is not in the book, but in general. Let's go back to the calculus 1 version of chain rule. Is that right? And now we go to different version of multivariable calculus. I'll go back to a previous section. Remember the Jacobian matrix. We can write like that. And the Jacobian matrix, not only that, we can write that as derivative of the function f. So that is the matrix. So df is the derivative in that form. Right. So this is the calculus 1 version of the chain rule. Now we have the tree diagram. It works, certainly works just fine, but now in general we can write like this too. So we have z as a function of x and y. So let's say we say z is the function of x and y, right? And then each one of them, x is a function of s and t. So let's say u of s and t, and v, and y is a function v, s and t. Let's put in a diagram. So the function z of x and y, we call that is a function f. And if we put together x and y as a function of s and t, we call this function g. So this is together is g. We can say xy equal to g of u, s and t. We can even write like that, right? So x and y is a function of s and t, and z is a function of x and y, like that. Right. Now, the Jacobian matrix, remember, the f is going to be equal to the matrix of f of x, f sub y, a row matrix. And this is a function of g. We can write dg. G has two component function, x and y. So first, we can say the first row is for x, second row for y. So the first one we can say derivative of u with respect to s, derivative of u with respect to t. Or we can even write derivative of x with respect to s and derivative of y with respect to t. When we write like this, it could be misleading, but we know x is a function of t and y is a function of t, like that. This will be x, sorry. So the first row is x, the second one is y. Right? So remember, each column corresponding to one variable, so s and t, and each row corresponding to each function, x and y. Function of x, function of y, so there's two rows. For z, there's only one function, so just one row. In that case, finally, we can say derivative, if we write z as a function of f, as a function of g of st, it is in this form. We say df dot dg, the product matrix, the matrix product of those two. So we write f of x, f of y, and then multiply by dg, x of s, x of t, y of s, y of t. Now multiply matrix row by column, and then row by column. We end up with this. So the chain rule in the matrix form, function multivariable, we can put in the matrix form, and we just do like this. Each component function corresponding to each row, and each column corresponding to each variable. So we can write this in matrix form. So derivative of z with respect to the first one is s, so we have f of x of s, plus f of y of s. So exactly that. And then row by column, we have derivative of z with respect to t. So certainly we can write that in the matrix form. However, this is not what written in the book. For a little more advanced, a little more general, we can use the matrix form. But for now, the diagram works just fine. So we can draw a diagram from the top function from the top variable to the bottom variable. Just trace, follow the tree from the top to the bottom. We will have it. So that should be easy. Right. Here's an example. Let w be a function of x, y, and z, and each one of them is a function of s and t. Draw a tree diagram. So that's the first thing we do when we have given the function. So we have w, a function of x, y, and z, so 3 variables. So there will be 3 branches. And each one of them is a function of s and t. So s, t, s, t, s, t. And what we asked to find is the derivative of w with respect to s. So we can go from w to s, w to s, from w to s. So we write the derivative of w with respect to s equal to w with respect to x, function of more than one variable, and then with x with respect to s. All of them are partial derivative because they have more than one variable. And then w to y, y to s, w to z, and then z to s. Simple enough, right? We just draw a tree diagram and follow from the top to the bottom. If we calculate, if we do that, make sure that everything must be in terms of s and t. So write the answer in terms of the bottom variables. Right, so that's very nice. It's not that complicated at all. Now we go to implicit differentiation. So implicit differentiation is different than what we do is we don't have the function equal to something. We just have an equation. So what we do is we take the derivative of an equation. And derivative of y with respect to x is negative derivative, partial derivative of x with respect to y, negative. Notice that switching in variables, y over x, x over y, and that's the negative. Right. Let's look at first example. Find dy over dx of this. So what we have here is an equation equal to 0. Equal to 0 or not, it doesn't matter. It could be equal to any constant. Any constant is fine. But here we just say move everything on one side equal to 0, right? Now, of course, that is the formula. Negative f sub x or f sub y. Now we just find the derivative of f with respect to x. Derivative of x, f with respect to x. Here we have the function here, sine. So there's x in it, and there's x in it. This one, y squared, is a constant. Derivative of constant with respect to x is going to be 0. So derivative of sine is cosine of the parentheses. Doesn't matter what the parentheses is. We're going to take derivative with respect to x. So this is the chain rule. Derivative of sine of xy. 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 Derivative of this is 0 because there's no x in it. Everything else is constant. So this is constant. So that's 0. derivative of negative x with respect to x is negative 1. So we have cosine of xy, derivative of xy with respect to x is what? With respect to x, y is a constant. So we just have a constant times x. It's just like derivative of 3x with respect to x. It's just a constant. Y here is just like a constant. So derivative of this, of course, is going to be 3 because derivative of x is 1. So we just have y because x is constant. I mean because y is a constant with respect to x. Sorry, I should say that. So it's just equal to y cosine of xy minus 1. So that's derivative of f with respect to x. Now derivative of f with respect to y. So same thing here. This is the chain rule. Cosine of something and derivative of that with respect to y. Doesn't matter what inside of that parentheses. It happen to be xy. Derivative of this with respect to y is going to be 2 pi y. And derivative of negative x with respect to y, that is constant with respect to y, so it's going to be 0. So we have cosine of xy. Derivative of xy with respect to y. With respect to y, x is a constant. And once again, we just have like, we treat x as a constant. X is a constant. And then plus 2 pi y. So we're going to have x cosine of xy plus 2 pi y. So derivative with respect to x, y cosine xy minus 1. And then over this, x cosine xy plus 2 pi y. So that's what we have. Nice enough, right? Before we go to the next example, I just want to go back to the previous section. I remember the application about the ideal gas. This is on page 63, section 15.3, previous section. So if we have PV equal to T, now we do differently, so let's use different color. If we have PV equal to KT, move everything on one side, and we're going to have F equal to PV minus KT equal to 0. Right, so we have this equation turn into that. Now, from here we can say derivative of F with respect to P, everything else constant. With respect to P, so just V. And derivative of F with respect to V is P. Right? And then so PV, derivative of P with respect to V, partial derivative of P with respect to V is going to be negative. We're going to switch the variable V F of P. So negative V derivative with respect to V is P, and derivative with respect to P is V. And we say that doesn't look like that. But that's fine because in this formula there's no P in it. So if we solve for P from here, we can say P is equal to what? V over KT over V. And we substitute this into P. So we'll have V at the bottom. On the top, that's negative KT over V. And multiply reciprocal, we're going to have negative KT over V squared. So exactly what we have over there. But we use implicit differentiation. So move everything on one side, get the function. And we have the equation equal to 0, and we let that equal to f. And use partial derivative, and we will do this. Notice that this one P is, I use partial derivative because there are 3 variables here, P, V, and T. So that should be partial derivative because we assume that P is a function of V and T. So that is consistent to what we have earlier. Right, just move everything on one side, let that equal to 0, and the whole thing will equal to capital F, and take the partial derivative with that and use the formulas. Right. Next, suppose Z is a function of x and y, find partial derivative of Z with respect to x. So there are 2 variables here, Z and x. So we go with partial derivative. First, this equal to 0, which is good. We're going to make that equal to the function of 3 variables, x, y, and z. Make that equal to. But even more precise, we have z is a function of x and y, so we can write like this: f of x, y, and z is a function of x and y. We can even say z is a function of x and y equal to x cubed y plus e to the z y minus cosine y plus 3. Right, now this is a little bit different than the partial derivative we have earlier. We won't write z as a function of x and y and we use the chain rule. We're not going to do that. We're just going to keep z as is. Now there's 2 variables, z and x, so we just take partial derivative of f with respect to z. With respect to z, this is a constant. Yeah, we can write like that, but just focus on the first one then. Focus on this. Yeah, it's really middle. It could be more confusing when you write like that. Alright, so derivative of that with respect to z. This is the only term that has z in it. Everything else has no z, so everything else are constant. Derivative, that is 0, that is 0, that is 0. We just have this. Derivative of e to the z is still e to the z. Y is a constant, stick to it. So that's all we have. Derivative of f with respect to z. Next, derivative of f with respect to x. This one have x. Derivative is 3x squared. Derivative of y, 3x squared. Y is a constant. We stick to it. And that's all x we have. So derivative of z with respect to x be equal to negative f of x. Notice the variable have to switch, f of x over f of z, negative 3x squared y over e to the z y. Right. once again, sorry, this will be misleading and kind of confusing if I just write like this. So that's not right like that. If you write like that, we can do it differently and we should get the same result. Right, I'm going to write like this again. Function of x and y. So we have x cubed y e to the z. Z here is the function of x and y, and there's y. I'm going to write like that. Now, I'll take derivative of everything with respect to x, because that's what we want, right? Derivative with respect to x. So we take derivative with respect to x. This gives us 3x square y. Derivative with respect to x. Let's just spell it out. Differentiate with respect to x will be 3x squared y. Now z is a function of x, so certainly z have x in it. So we're going to write plus e to the z and then we have z with respect to x. Stick the constant y to it. Right. Once again, it might be misleading to write like this. Let me rewrite this, albeit make more sense. So just write x cubed y plus ez y minus cosine y plus 3. Right, sorry. First of all, don't write this if we're going to use f as a function. Yeah, don't write that at all. That's extremely misleading. Now notice that z is a function of x. Now focus on this. Z is a function of x and y. So I'm going to put the parentheses around it. And I'm going to use the chain rule. Now differentiate with respect to x. That gives us 3x squared y. Now derivative of e to the z is going to be the same thing, right? And then we take derivative of that with respect to x. It just happened that z is inside the parentheses. We do that because z have x in it, so we put the parentheses. The y here is constant, still there. That derivative of constant 0, derivative of constant 0. So that's what we have. So I have 3x squared y plus e to the z. This term here becomes derivative of z with respect to x, y equal to 0, and then we solve for that. Move that to the other side and then divide, which is exactly what we have here. So where there we just write the equation, take derivative with respect to x, and be mindful that we assume that z is a function of x and y, so we put the parentheses around that and we use the chain rule. Either we do that or we just write everything in terms of f as a function of f, and we take partial derivative with respect to z with respect to x, and then we use the formula. Notice that the variable we switch, and that's a negative sign. Don't write like this, it is misleading. So ignore that. Either way, we should have that. Right, or we just take derivative directly. Right, now we go to more exercise. So this is just a review of what we learned. Find derivative of dw with respect to t. For derivative of w with respect to t, where w is this, and each one of them is a function of t. So we start with the diagram. Start with w. W has 3 variables, x, y, and z. 3 branches. X, y, and z. and each one is a function of t. So the partial derivative of w with respect to t. Now, the reason we use d and not the wiggly d, because there's only one variable at the bottom. So that's just dt. If we have two variables at the bottom, then that will be partial derivative. Like this, if there's s and t at the bottom, they're partial derivative. If there's just t at the bottom, this is the derivative. Right, so from w to t, we can go from w to x, and then from x to t, from w to y, and then from y to t, and from w to z, and then from z to t. W is a function of x, y, and z. Right. Derivative of this with respect to x, y, and sine z is constant. Derivative of x is 1, and then just have y sine z. Derivative of x with respect to t. Derivative of x with respect to t be 2t. Derivative of derivative of w with respect to y, or derivative of that is going to be x sine z. Those are constant. Derivative of z, y is 1. Derivative of y with respect to t be 12t squared. And derivative of w with respect to z will be xy. Derivative of sine z is cosine z. Xy just constant. And then derivative of z with respect to t, derivative of that with respect to t is just 1, right? Multiply it out, and then finally put t in for it. Right, so first I'm going to put 2t in front. Y sine z, and then 12t squared x sine z, and then xy cosine z. Right, and then just substituting x, y, and z into this. So 2t, y is 4t cubed, and z is t plus 1. And then 12t squared, x is t squared, sine z is t plus 1. And then xy, x is t squared, y 4t cubed, cosine of z t plus 1. Yeah, just substitute all of that in. I run out of space, but certainly we can combine those terms. It's no big deal. Yeah, just notice that we can just do that. Right, next, let w be a function of z, and z be a function of x and y, and each x and y is a function of t. Right, so start with w is a function of z, and z is a function of x and y. And each one of them is a function of t. Right, so that's what we have for the 3. So only one variable at the bottom, so it's going to be just derivative. So we can go from W to Z, Z to X, and then X to T. So there are three of them. First one, W to Z, there's only one path, only one variable. So this is going to be just the derivative, just the notation thing. Next, from Z to X, from Z there are two variables, X and Y. So if we go from Z to X, this is partial derivative. And then from X to T, there's only one path. So just the derivative. And now if we want to go the other round, Z to X, W to Z, Z to Y, and then Y to T. W to Z, there's only one path, so regular derivative. Z to Y, there are two possible ways from Z. Partial derivative, because there are two variables. And then the dy over t, there's only one path from y to t, so derivative. Right. So we just draw a tree diagram, certainly works. Or we can use the matrix form, which is a little more advanced, but that certainly works as well. Right, so that's just the chain rule. Now what we have here is, let x squared plus 4y is equal to 5x, 5 dy over dx. Right. So what is the difference between this one and the previous one? The difference here is that we have an equation, as opposed to we have something as a function of something else, right? So we don't have the function here, we have equation. So how do we do that? Usually if we have an equation, this is implicit differentiation. So we have dy over dx. If we can say that is going to be negative f of x over f of y. So that is implicit differentiation. Right, so of course when we have this, move everything on one side, make that equal to 0, and that's a function, right? That certainly works. However, it can be even better. Notice that when we have the equation with the square root, I certainly don't like the square root. Derivative look messy. Right, so why don't we square both sides here? So we have x squared plus 4y equal to 5x squared. So we square both sides. The square undo the square root. Yeah, that cancels out. So we have x squared plus 4y and then equal to 25x squared. Right, so that's still an equation, which is good. Move everything on one side, and that equal to f x squared plus 4y minus 25x squared. That is a lot better without the square root. Now, we're just going to find the partial of f with respect to x, which is 2x, that one's 0, that one's 50x. Derivative with respect to y, only this one have y. That's all we have. And finally, dy over dx is equal to negative f of x over f of y, negative 2x I should just subtract them, right? Negative 48x. Yeah, just combine them. Yeah, I should do that from the beginning. Anyway, still fine. And then divide by f of y, which is 4. So we have 12x. If we move everything on one side, that will be equal to 0. So we need the function equal to 0 to do this. In order to do implicit differentiation, we need to have the equation equal to 0, and we make one left hand side of that equal to f. And that's exactly what we do here. Of course, if from here we solve for y, y will be equal to positive 6x squared, take derivative, give us 12x. So that also works. Right? What I mean is this: if we solve for y, and then derivative, should be easy, very easy, right? But in this case, we do the implicit differentiation. Implicit differentiation is that we move everything on one side, make that equal to 0 on one side, and the left hand side equal to f, and then take derivative with respect to x, with respect to y, and then use implicit differentiation formula. We have that. This case is simple enough when we can solve for y, but sometimes we won't be able to solve for y like this. Right, next, it's kind of the same thing. Suppose xy plus xz squared plus yz cubed is equal to 5. Now find partial derivative of z with respect to x and partial derivative of z with respect to y. So just like the previous problem, move everything one side, make the right hand side equal to 0. So one side is 0, the other side is equal to f. Let's move the 5 to the other side. We just keep it if we want to, because the derivative of 5 is 0. But we make that equal to 0, and we're going to make the left hand side equal to f. Here we have z and x, so let's find the derivative with respect to x. Derivative with respect to x of this is derivative with respect to x is 1, y is a constant. Derivative with respect to x is 1, z squared is a constant. And that's it. Derivative of this, there's no x here. Derivative of a constant is 0. Derivative of constant is 0. So that's all we have. Now we also have z. So take derivative with respect to z. No z here. That's 0. There's a z there. Derivative of 2z squared is 2z. And derivative of z cubed is 3z squared. And the constant y is still there. Right. So we have 2xz 3yz squared. So we have partial derivative of z with respect to x according to the implicit differentiation will be negative. Make sure you switch the variable. So z over x, x over z, but with the negative. Right. Derivative with respect to x, y plus z squared. Derivative of z with respect to z is that 2xz plus 3yz squared. Just like that, right? Right. Next we have partial derivative of z with respect to y. So we only have z. We only did find derivative with respect to z of f with respect to z. Now we just need the variable y. So we find f of y. There's a y here. Derivative of, and then x is a constant. Derivative of y is 1. That one is constant because there's no y. Derivative of that is 0. Yz cubed. Derivative of y is 1. Z cubed is a constant. 5 is a constant. So that's all we have. X plus z cubed. And finally, derivative of z with respect to y will be negative, and we switch z over y, we have y over z. So this is negative. Derivative with respect to y is this, x plus z cubed over derivative with respect to z, which is this. Right, so that's all we have. Right, so in this section I did not do a lot of example, but I think we cover everything. So the chain rule, very important. Make sure you draw the tree diagram before we find the derivative, and make sure if we have two branches, that partial derivative. If we have one branch, that is just derivative. And then implicit differentiation, just move everything on one side. One side is 0, the other side is f of xy, and then find the partial derivative and use the formula. Notice there's a minus and the variable switch. Right. So that's all I want to cover for this section. For this section, the homework will be a little more than the other section, especially 15.3 and 15.4. Take derivative and then the chain rule. Those are very important. So you expect to have a lot more homework for those sections. But anyway, I'm going to stop here. As always, thank you for watching.